Unlike the Riemann integral, we do not require the domain of definition of a function that is Lebesgue integrable to be a finite interval. It could very well be the whole of R itself. How do we check whether a function defined on an unbounded interval is Lebesgue integrable? Well, the following theorem gives one way of doing it, and it will prove to be quite useful. Theorem. Let f from closed A open infinity to R be a function. Suppose for each b in R, f restricted to this closed AB is an element of L of AB. That is, on any closed interval, closed and bounded interval, when you restrict f to that, f is Lebesgue integrable. And further assume there exists a constant m greater than 0 such that integral a to b of the absolute value of f is less than or equal to m whenever b is greater than or equal to a. So independent of the choice of b, suppose the integral of the absolute value of f is always bounded above by m. Then f is actually an element of LA plus infinity. It's Lebesgue integrable, and as you can expect, the integral of f a to infinity is nothing but limit b going to infinity of integral a to b f. Okay, so you can obtain the Lebesgue integral of the function f on the whole interval all the way up to infinity as a limit of its integral values on finite portions. This is sort of intuitive, but it still requires a proof. Let's move on to the proof. This is going to be yet another application of Levy's monotone convergence theorem. So what we do is we take Bn increasing to plus infinity, Bn greater than or equal to a. Take some sequence of real numbers greater than or equal to a that increases to plus infinity. Okay. Now what we do is we restrict f to these intervals a, bn and consider them as a sequence of functions fn. That is, define fn of x by definition to be f of x if a is less than or equal to x is less than or equal to bn, and 0 if x is greater than bn. Okay. Now each fn is Lebesgue integrable on the interval I, okay, where I is a infinity. Why is this the case? Well, think about it. We already know that when you restrict f to this interval a, bn, it's going to be Lebesgue integrable. Outside that interval, it's 0. Therefore, it's got to be Lebesgue integrable on the whole of I. I will leave it to you to work out the details. Okay. And it is clear that fn, let me say I defined to be a infinity. It is clear that fn converges to f on I. In fact, fn increases to f on I. Okay. Furthermore, integral over I of mod fn is equal to integral over a to b of mod fn, which is going to be less than or equal to m by hypothesis. by hypothesis. Okay, consequently the sequence A to B mod Fn, this collection is a bounded set. Okay, this means by monotone convergence theorem, mod Fn converges, of course it converges to mod F, and this mod F is going to be Lebesgue integrable, and integral of mod F is nothing but limit Bn or n going to infinity An to Bn mod Fn. Okay, excellent. Now what we essentially have is Fn is less than or equal to mod F, and mod F is an element of L of I, right? Which means that by dominated convergence theorem, the limit function of f, which is nothing but limit function of Fn, which is nothing but f, is also an element of L of I. Okay, and furthermore we have limit n going to infinity of integral a to bn f is nothing but integral a to plus infinity of f. Again, this is also by dominated convergence theorem. So this shows that you can obtain the Lebesgue integral of f on that half infinite interval by just taking some sequence. It doesn't matter what sequence bn you take, and taking the integrals and taking the limit. As a corollary, we also get that irrespective of what sequence you choose, these integral values will converge to the same value. Okay, analogously we can treat functions defined on minus infinity a exactly in the same way. You just consider a sequence bn that now decreases to minus infinity, and you get almost the same result. You will get integral minus infinity to a of f is limit c going to minus infinity integral c to a f. Okay, so of course you have to assume that the integral of a mod f is less than or equal to m, no matter what choice of c you choose. So you have to put an analogous hypothesis on the boundedness of the absolute value integral. Okay, now together if you have a function f from R to R, then with the hypothesis that for each a comma b in R, a less than or equal to b, if we have integral a to b mod f is less than or equal to m, greater than 0, fixed quantity, then we can combine the theorem that we have and the analogous version for the negative infinity interval. We can combine both of them and write minus infinity to infinity of f is nothing but limit c going to minus infinity integral c to a f plus limit b going to plus infinity integral a to b f. Okay, and as a consequence we also get that it doesn't matter which point you break up. I mean, typically what we will do is we will break up this integral into these two pieces by choosing this point a to be the problematic point. That's usually how it is done. Here as a consequence we get that it really doesn't matter which point you choose. We will get that integral minus infinity to infinity f can be broken down into two integrals and taking the limits. Okay, let's work out an example. Let's see an example of a function that is genuinely defined on the whole of R and is still Lebesgue integrable. consider the function f of x equal to 1 by 1 plus x squared. Okay, claim is f is Lebesgue integrable on the whole of R. So here is an example of a function that is nowhere 0 in fact. It is always going to take a positive value throughout the real line, yet the integral is very much defined and it's a finite quantity. Well, what do you do when you fix a and b and consider integral a to be 1 by 1 plus x squared? By high school integration, you know that this is going to be just tan inverse b minus tan inverse a. This is from high school calculus, and the range of the inverse trigonometric functions is from minus pi by 2 to pi by 2. So the maximum value of this difference can be pi. So the integral a to b 1 by 1 plus x squared is always going to be bounded by pi. So by the previous result, 1 by 1 plus x squared is in L of R. Okay. Furthermore, by that fact that you can break up the integrals, you can write this as limit let's say b going to infinity minus infinity integral b to 0 of 1 by 1 plus x squared plus integral 0 to a limit a going to infinity of 1 by 1 plus x squared. Okay, and this would just give pi from the basic properties of the tan function. So we have found that the function 1 by 1 plus x squared is Lebesgue integrable on R, and its integral value is exactly pi. So this is sort of a stopgap video where we see how you can find out the Lebesgue integral on unbounded intervals. This is a course on real analysis, and you have just watched the video on the Lebesgue integral on unbounded intervals.